Now let's build in some more of the notation and nomenclature that we have associated with resonance structures, and also think a little bit about where we're saying the electron will lie. Now, what we're saying is that it's spending equal time in either of these two forms. Now, we'll also see cases where we can have more than one form that are in resonance, and they're not always going to be totally equivalent. Sometimes there's ones that are, pretty poor, but there's others that are very good in the same molecule. We'll see examples of that later too. So we can draw it like this, where we show a resonance bond. We can still show electron pairs, but we often won't because it gets really confusing there. The other thing people will try to do there is they'll actually try to come up with a way to count the electrons. You will see cases, if you search around on the internet, where people explain how you can try to count the octet based on a resonance structure. Great. We can add an extra whole set of layer of notation and rules and counting and all that. Or you can just count one of the two precursors. Or you can just freeze frame it, where you say, okay, well, if it's spending half of the time here and half the time here, let me just go ahead and erase one of these. And we'll just pretend like it's all the way in the other spot. Easier to count. So do it the easy way. I'm not going to add it in the complication of that kind of a notation. Now, here's our notation and names for these things. A partial bond, that's the dotted line that you see. In this case, it's spending half of the time here and half of the time there. So its bond order will be 1.5. If I had something like, I'm just going to make something up here. I don't think this is actually possible, but I just want to show something real fast. If you were having a bond that was in resonance here, here, and here, then that would be 1/3 in each place. So you'd have a bond order of 1.33, or 1.3 if you're just doing it really fast and simple. So bond orders are not locked in just at the 1/2 mark. You can have them in any iteration in between. Now, since this bond is spending time in both of these locations, it's been delocalized. In other words, it's not just between two atoms. This bond is actually over all three of these atoms in the case. And delocalized bonds are important because they add a lot of strength and stability, and also a little bit of rigidity, we'll find out when we talk about three-dimensional structures. Now, I really want to encourage you, don't try counting it on this form. I've said it so many times now, I think you're picking up that I'm pretty serious about it. It's a messy, messy business to try to count octets on a resonance form. Now, the other thing I want to point out is that the whole thing will be stabilized by these delocalized bonds, in part because you have fewer electron-electron interactions. This orbital, I'll point that out, you can make an orbital for this single bond that's spread out. Your delocalized bond is now an orbital that is not just between one atom or two atoms. It's now an orbital spread over 3, could be even more atoms. And that's going to be something that really helps glue the whole thing together. And so that's going to be an example of a delocalized bond.